Hello, everyone. Today we are presenting our Automotive Networks project. My teammates are Sebastían Melendez, my person, José María Galeana, and Emilio Rafael García. Well, we are implementing a multiple ECOS electronic control unit simulation using the industry standard vector camera platform. Our project simulates modern vehicle electronic system using control area network or Canoe protocol. The backbone of automotive communication, we have developed two interconnected systems that demonstrate that how distributed ECUs work together to create a cohesive vehicle experience. Well, for the first part, by main control and door system, we created a two-node system with a main control ECU and doors ECU. This basic configuration implements fundamental vehicle controls. That's like ignition status switching, door locking and unlocking, window position control with up and down movements. The system demonstrates the event-driven nature of automotive communication. When you press a button on the interface panel, environment variables trigger CAN message that transmit across the network to the appropriate control unit. This panel will demonstrate deeply by my teammate Emilio Rafael.
So I'm gonna show you the part one of our project, and it's over here. First, I'm gonna show the panels that I implemented. First is the ignition panel or control panel that have the ignition button, the lock door button, and the window up or down. Next to this is the window aperture gauge meter, and basically this is how it works. So if the ignition button is off, these controls, the window control will not work. But if the ignition button is on, the windows will start rising or going down from these buttons. Also is the lock door button, and we can see this on the trace panel. It's here. As we can see, if the ignition it's off, there's a 0 over here. It's on, there's a 2. Lock doors, it activates the ignition status, the locking control RQ, locking system state, and here the window request and window state. So the window request is if one of the buttons are requested, and the window state is the position of the window that goes from 0 to 15. Now we can see the a little bit the KPL codes. So we basically put all the messages here and put 4 timers for the main control CAN. We initialize the environment variables. Ignition start. If ignition start is 1, it changed the data link code to 1. Here's the signal to 1 also, and the same for basically all the other ones, except for window up that it's here we put a timer to move because the timer is for the gauge meter panel that shows the window aperture, and for door scan we basically put all the messages that we see on the trace panel for window RQ, window status, and yes, basically that's the part one. Now my teammate Sebastian, gonna show you the part two.
Well, for the part two, illustrate the indicator system. We expanded to a 5-node network implementing a car indicator system. It is like a central control node from left and right indicators IQs, rear left and right indicators IQs. Well, this system demonstrates 3 KE operating modes: left turn signal, right turn signal, hazard warning, all indicators blinking like an alarm. We implemented a synchronized 1 Hz blinking frequency across all nodes, showcasing how distributed IQs maintaining timing consistency. Well, I'm gonna pass the word to Sebastian to explain it deeply.
Well, as my partner say, we expand to 5 EQs. Here we have the 5 EQs and the central EQ. We have this panel for the blinking. This is the alarm. When we run, we can see the alarm. All lights are blinking. When we shut down, we can put the turn left, and just the left are turned on. And it's the same with the turn right. The right are blinking. And we see the CAPL, we can see the main EQ. We have we put 3 messages important. That is the alarm turn left and turn right. We initialize the alarm on the sys bar alarm button. We make an instruction that are sending the message in the CAN bus, and it's the same with the left button and the right button. In each AQ we have the message reading alarm. If this alarm, they are sending to the timer 1 on the when in this we can configure the time of blinking, and we have the timer in the timer 1, that is the alarm button. We turn the lights and sending to the timer 2. The timer 2 are turning on the lights and return to timer 1. Timer 1 put on off the LEDs, and it's the same with the right EQ and the turn right, and the left is the same. In the back is the same, and we are sending the word to my partner to explain the third part.
Well, about the third part, it's part 2 extended monthly. This is mirror control. We then extended the system to include mirror positive controls like left, right mirror selection, 4-way directional adjustment, position memory functionality, and real-time position visualization. This extension demonstrates how CAN networks enable incremental future development. We were able to add new functionality without rebuilding this existing system. This is going to be explained deeply for, again, Sebastían.
Well, in this second part extended, we have one panel to control the left mirror and right mirror that is controlled by the turn right front EQ and turn left front EQ. When we have a main button that are switching in the left mirror is off, and the right mirror, and when we click this, we can turn on the LED that are telling us the right mirror is listening, and when we put it on up, the 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 reading are going to 0, that is totally up, and down is going to the 100, that is totally down, and it's the same with the vertical, are going to the top left and top right. And when we are switching, just these two readers are going up and down, and it's the same with the left, and that's all. Thank you. We are showing the CAPL code. In this, the main control are sending the sys bar, are reading the sys bar up, and we are sending the message on UPM, that is in our database, and the same is for down and right and left. The corresponding echoes are listening this message, and on the UPM message are reading, they are going to the timer tree. The timer tree are filtering the information, and when the mirror start is up and mirror left is listening, they are subtracting one variable, the horizontal right, and sending to the timer tree. Timer tree is reading again and is the same to the 0. And for the other echo is the same. And they are listening the message and sending to the timer 4 or 3. And that's all.
Well, as a key achievement, we can relate that this system demonstrates several critical aspects of automotive electronics as hierarchical networks architecture, message-based communication, combined time-triggered and event-triggered behaviors, modular system design, and realistic user interface development. And as a conclusion, through this project, we have gained practical experience with automotive networks principles that are directly applicable to real-world vehicle systems. The modular approach we have used could be extended to include additional vehicle functions like limit control, engine management, or advanced driver assistance systems. This is all our project as Automotive Networks. Thanks for watching.